잠시만요. Yeah. I'm looking for speaker. Chishan Yan. Not yet. Cheng Jia. Oh, you are here, right? Anil Kanduri. Anil Kanduri is. Oh, you are here. Okay, I'm looking for second speaker. Chi Xuan Yan. Okay, since time is up, let's start Codes session 2. Good afternoon, welcome everyone to this session. The title, Advanced Trends in Efficient Inference. In this session, we will have 3 regular papers and 1 late-breaking paper. So for regular papers, the presentation time is 25 minutes. So 20 minutes presentation plus 5 minutes Q&A maybe. Okay, let me introduce the first speaker. First speaker is Hashi Sharma. Hashi is currently a PhD candidate in Washington State University. He did his undergrad from NSIT Delhi University in Delhi, India. Hashi has worked as a machine learning engineer for AR applications before starting his PhD. Goal of his research is to develop principled AI-driven design paradigms in huge search spaces for efficient chip design built toward high-impact applications. Okay, let's welcome speaker.
Hi, am I audible? Good afternoon, everyone. My name is Harsh, and with my advisor and collaborators from Washington State University, Topol Labs, and University of Wisconsin-Madison, would like to present our work called Flow-Rates for Chiplets, which is a data flow-aware, high-performance, and energy-efficient network on interposer for CNN inference tasks. Firstly, I would like to lay down an agenda for this presentation. I would go over the motivation and related work. Then I'll talk about this workload-aware network on interposer design, where we'll talk about the space filling curve for this network on interposer design, and talk about the flow rate architecture, which is within which we talk about the hardware software co-design, which is the neural layer to chiplet mapping, and the overall flow rate architecture design. Then we go over the explainability idea of why this works better by showing the NOI, the network on interposers, router and link configuration, the performance analysis, and finally we conclude the presentation with the vision forward. So as it has been highlighted in multiple technology roadmap that it is very evident that industry is moving towards smaller nodes, and hence the yield is decreasing, where the byproduct is manufacturing of a larger chip is not economical. As you can see over here, in die, a wafer of about 3 centimeter, we have 10 millimeter square die with about 33% yield, which means only 1 out of 3 chips are going to be fully functional. However, there have been some innovations within 3D stacking, but it gives some of the issues which are currently faced, like the temperature hotspot and additional dollar cost around the routers when we have these 3D layers shown in purple, which are called as the keep out region. So why chiplet in the first place? So we'll talk about what is chiplet. So we take this bigger chip and we divide it into smaller dies, which are fabricated on a single wafer. As you see over here in this figure, we have white chiplets. Each of them have their own router, and they're connected by these links, which are double arrowed links. So it's a compact scale out implementation, and they're connected through this network, the NOI that I was talking about earlier. However, in this case, because the yield improves, because the defects are amortized on a smaller die, so it is an economical manufacturing process, but it has issues now that the chiplets are physically far apart. You can see the scalable communication due to this larger physical distance becomes an issue. There might be thermal issues within the technology node that we're using and defects. But here, we should kind of think about how industry is approaching this paradigm shift. So the biggest issue of all, the challenge, is the communication, where it is highlighted here, one of the toy example for chiplet, where system scalability and fabrication costs actually hinders the widespread adoption, where the obvious reasons are poor technology scaling as the wire length increases. We have larger physical distance, as we can see by these pink nodes, and it's overall a power constrained environment. However, an efficient NOI, the network on interposer, can solve this problem. But we need to have this idea baked in, which is performance should not be compromised. And we should maximize energy saving as the system size scales, because we expect the number of chiplets are going to increase. Additionally, NOI consumes 80% of the total area of this chiplet-based system, and energy consumption is the bottleneck of the NOI. So there's an inherent need of scalable architectures. It's immediately important we address that. So there have been related work in this field, starting with Pascal Vivet's work called Intact, which is a 96 chiplet system which put the baseline for lower latency interconnects. Next was by Stanford and NVIDIA joint contribution called Simba. Simba is a 36 chiplet DL application system which was introducing tiling optimization in the first place, where they were creating this application specific NOI on the 2D mesh. Then there's a family of topologies which are misaligned called Kite, where we have skip connections being introduced like the purple or the orange one, but is primarily a torus-based architecture. And then there's SIAM, which was one of the cases paper in 2021. It's a scalable evaluation framework in 2.5D system. It assumes a 2D mesh on the NOI. None of these work are DL workload aware. So we don't know what we might be expecting as the time goes on. There might be an imaginary net. So to solve that problem, we had an application-specific architecture in last year cases called SWAP, which assumes an irregular NOI, where the NOI placement and the core placement depends on what is the traffic. But the issue is, in case of concurrent CNN tasks, which are at data center scale, none of the previous workloads actually solve that problem, but FlowRed effectively, by its inherent NOI that we'll see later in a few slides, kind of tackles that problem. So our novel contributions, we're the first workload-aware NOI for this data center scale workload that you might expect in Google, Facebook, and beyond. We evaluate up to 8.8 billion parameters, and we use RERAM-based PIM architecture. Here, I would like to make it clear that this NOI architecture is agnostic, and any of the technology node could have been used. We use space filling curve-based NOI that I'll talk about why space filling curve and what they are. We enhance the performance and lower the energy consumption, and we have this inherently versatile NOI for deep learning workloads which are beyond CNNs. We use a hardware-software co-design, kind of good for this track, and also we lower the fabrication cost that we talk about later. So it's a critical step towards making chiplet-based main ecosystem design more accessible. So let's talk about this workload-aware NOI and space filling curve. So first, I would like to bring out a similarity to a human brain, a neuromorphic similarity. Most of you might be aware that we have multiple different parts in our brain which are supposedly doing different tasks. They might be happening concurrently and within one lobe, for example, the frontal lobe, which is for visual recognition, or the occipital, which is for spatial recognition or depth analysis, that might be working concurrently. So we have multiple tasks which are happening, which might have within serial execution. And we have concurrent execution of tasks based on what type it is. So the space filling curve, as an idea, represents a class of algorithms which basically maps something in 2D using a one-dimensional space. It generates a locality preserving data structure, which will make more sense once we look at the physical realization in the next slide. And SFC traverses the area with no closed loops. So kind of looking at this architecture as an example, we have a neuromorphic idea kind of baked in as a toy example, FlowRed being on top of brain. So let's look at the physical realization that I was talking about. Here you can see that we have a hierarchical top level network. And there are multiple SFCs of different color, from purple, red, whatever. We have links between neighboring chiplet along this contiguous SFC path. Then we have inter-SFC link, which we call as the top level network. And then we have intra-SFC. So there are two parts where this problem of actually accelerating data center scale inference of CNNs, we have this one common property that no matter what, the activations go from Li to Li plus 1. We might have skip connections that we'll actually address later in the next few slides, and we maintain a contiguity along the NOI path. Our design considers a head and a tail. So a head of a SFC is where it starts, and the tail is where it actually ends. And then we have a trade-off that, okay, what are the number of SFCs and how long each of the SFC is? And we have this hierarchical structure. You can see it could easily be like a traveling salesman problem, where you start at one end and you have to end back at the same place. So we kind of solve it with engineering principles of symmetry and decomposition, but there's a trade-off between what are the sizes. So the common property that I was highlighting as have been in a lot of papers for DenseNet and CNNs, we have an input image, convolution layer pooling. We always have this activations from Li to Li+1, which is primary. Our experimental results have included DenseNet, ResNets in multiple different scenarios. And maintaining this contiguity on the NOI actually solves the problem very effectively. So here I can give an example to last year's cases paper, which is swap, where obviously when we are mapping something which is runtime, we were not optimized for it before. So here we can see that we have unconnected islands which are created. So the left one is one example of swap, and the right one is the floret architecture that I'll go over one by one, making the similarity and the differences. So in case of swap, we have unconnected islands. The reason is we are trying to map greedily. We want to have smallest possible path between each of these communicating chiplets. In floret, we map the layers according to the Hamiltonian path, which is along the SFC, like starting from H1, go to T1, going on H2 to T2, and we come back to the same H1 when we proceed along this path. The benefit is, in case if the workload is much bigger than what our system can actually serve, we will basically be on the chiplet that is going to be the next available resource. So the chiplet resource becomes available as new layer allocation starts. So during the mapping, if we reach one of the tail, we have more than one option. So in case if there's inherent redundancy in the system, where if the yellow link is broken and we cannot use the section of chiplet, so we have introduced this inherent redundancy that we get as a byproduct in the system, which gives it that mapping benefits. So how do we find the optimal number of SFC? The idea is that we reduce the average number of hops between tail of one SFC and the head of the other SFC. The idea is that once we are on a given tail, we want to go reach the next possible head in shortest amount of time. The H average is calculated for all of these head-tail pair. And multiple SFCs are introducing the redundancy, but if one of the SFC is longer, then might be the resource might be wasted. So we have this trade-off that what should be the size and what should be the number of SFC. Another benefit is the top level network should not be big enough, because that's where we have the issues coming in. So the optimal number of SFC when we analyze for 36, 64, 81, and 100 chiplet system in this work, we lie between 4 to 6. Now, one question might be that one of the SFC could have been longer and other could be shorter. So we do like a simpler analysis on 36 chiplet system where we see equal SFC actually performs better because we have more homogeneous design. So latency comparison is shown where equal length actually improves when compared to an unequal length SFC within the system, which is like a basis for creating this floret architecture that we'll see. Again, the balance between the size, psi of each of the SFC and the number of SFCs. So as we can already see that because we have this floret architecture where we are just connecting one of the chiplet to one of its predecessor and the next one, we have the smaller router ports, kind of the explainability idea of why this works better. We can see all the other architecture, kite, SIAM, swap, and floret, where we have the number of routers being smaller. So the peak of floret in router port configuration move towards the left, where we have mostly 2 routers, the idea, and 3 in case of inter SFC. So we can give that redundancy. But that is not just enough. We also need to look at how many links are there and what are the length of these links, because it is crucial to consider what is the link length between these routers. Now we are physically far apart. So swap has smaller routers, but not all links are necessarily single hop because we have these bypass kind of. So we also introduce some longer links in case of swap, which could be 4 or 5 hops. Floret mainly consists of routers with fewer ports, and all the links are single hop that we show in the figure. So going on the fabrication cost aspect of it, the fabrication cost is a function of number of routers and the link, where the area of the NOI, which is going to be between area of the router and area of these links, becomes the part. In SFC, there are 2 parts, the hierarchical top level network, and we have the inter SFC and the intra, which are the 2 parts. So when we consider that, we can see the area finally, when we take a relative percentage, how much is the improvement, basically boils down between the difference of two NOI areas. So because we saw that figure about having smaller router ports, so our fabrication cost improves 80%, 60, and 49% with respect to counterparts, which are Kite, SIAM, and SWAP for 36 chiplet system. And this improvement actually increases because as the system size scales, flow rate is a linear, whereas other cases are not. We'll look into it later again when we talk about the conclusion. So let's talk about the performance analysis and look at where are these concurrent CNNs these are used. So real-time video analytics is a good example where you might have to do maybe use a ResNet 50 where you're doing a classification, and at the same time you need a segmentation model. So they're running concurrently within one single system. Other scenario might be cloud computing, which are used in the ensemble of models in case of Facebook and Google Photos, whoever has used. You have geotagging and image tagging where multiple CNNs are used together. So they're being done concurrently. One image is being used for one part of the ResNet, other is for DenseNet for, say, geotagging. The third example might be on edge computing where multiple CNNs can actually process locally. So as we go by, we don't need to send out a sensitive data to the cloud. So we consider these data sets to emulate the data center scale that we are talking about. So here you can see right from ResNets on CFAR 100 starting from 1 million so parameters, DenseNet VGG, up till we go up to ResNet as big as 890 parameters. This is just one single data set, but we actually emulate the whole scenario with taking the ensemble where they're running concurrently, as you can see in the biggest 8.8 billion parameter. If you remember these NNs, they just represent what they were. So we have 5 ResNet followed by some VGGs, multiple DenseNets. We use NVIDIA GRS parameter to implement all considered NOI to have this equivalent scenario. So there's a fair comparison. So the only difference is the network on interposer and also the mapping that we are doing. So here, let's look at the activation flow. Say, for example, I start mapping here at the red part. I continue at this point. I have an option. Maybe I can jump here if there was already a resource here, or we continue along this path. Using this as the bare bones structure, we ensure that if the incoming CNN requirement, some imaginary net with, I don't know, 1,000 layers might be introduced where we might have much more higher compute requirements that we have, we would be connecting. So if the layer first is mapped here and layer 15 is mapped on the last SFC after coming back, the next one will be getting available on the red part. So we always ensure that continuity, which we need when we are on the longer workload, and shorter, it works effectively due to the Li to Li plus 1. I have a visualization kind of showing what is the difference between the improved performance. So this is SIAM standard in NVIDIA, and also this is flow rate where you can see the less links. Let's look at power versus time of execution. For same workload, no pruning, no quantization, both of them have same traffic. You can see as the power consumption is higher in case of swap as the time of execution goes by. For a workload 7 with over 8.8 billion parameters, where you can see flow rate is already done, where SIAM is still running the exact same workload. So we save 1.8 times latency when compared to 2D mesh. And this area under the curve, as you can see, it's much lower, actually captures the energy consumption. So let's look at what were the actual numbers. So in case of 36 chiplet system, average performance with one example called Kite is 27%. We go up to 51, 82, and about 100% improvement due to this contiguity, which was not in the other scenarios, and having this hardware software co-design where we map along this software path. So because being data flow aware, we know about the data flow, what we might be expecting. Flow rate prioritizes the performance, whereas we are able to address these skip connections as we have considered because they flow through the NOI. Let's look at the energy savings, which is a byproduct of lower power consumption. We're having smaller routers where flow rate enables significant energy savings with about 2.7 times with respect to Kite. And with respect to swap, the last year cases paper, about 1.6. Having smaller routers with reduced number of links actually leads to this energy saving that we are seeing. So the fabrication cost quantification, we know NOI area is the function. We have smaller routers, smaller associated ports, and fewer links, and which is complementing the performance and energy. So I have this one figure over here for a 100 chiplet architecture, which is trying to capture the latency and the energy consumption for workload running on 100 chiplet system, where you can see the improvement is about 76% in latency, 50% in energy. The size of dot actually shows the power consumption. And the last part, because we have embodied carbon emission, which becomes a bigger problem as we go on the data center scale. this is obviously improving because now we have smaller NOI area. So as the system size scales, that becomes an important parameter to consider as the size increases. So we have reduced carbon emission on that front. So in conclusion, in the vision forward right now, we just considered homogeneous chiplets. We could have individual SFCs with this similar hierarchical top-level architecture where we have different types of CPU, GPU, DRAM and accelerators. And this scales better as we go into 3D due to this linear dependency. And there could be potential generalization as we have seen in these concurrent tasks on DL workloads. One example that I would give due to this contiguity and this heterogeneous, we can actually accelerate these newer multimodal architecture. For example, the feed-forward layer, which is within the transformer model, has a similar Li to Li+1 nature, where that transformer model's feed forward could effectively just be an SFC. So in summary, designing data center scale chiplet system poses significant communication challenges, obviously from the physical data, the physical distance between these chiplets. Floret is first workload aware NOI architecture for these data center scale deep learning workloads. The benefits are, higher performance, the reduced energy consumption. We lower the fabrication cost due to having smaller routers, and we also lower the carbon footprint as the system size scales. We see that improvement. Thank you. That was all for my presentation.
Okay, and now we have time for Q&A. So any questions? Okay.
This is working. One quick question regarding the performance and energy comparison. Correct me if I'm wrong, but I can basically overlay a space filling curve on top of mesh architecture, right?
Yes.
In which case the performance should be similar.
Right. In case of mesh, there's one dependency, because if we are doing the hardware software co-design, the bigger issue becomes the power consumption. So in case of mesh, we can still have, this is like an embedding. So on Kite also, which is one of the architecture, so where we can also create a space filling curve. Yeah. So it is agnostic to whatever. So
the performance should be similar in that case. Is that correct? Or do you expect a difference?
Yes, it depends on what kind of mapping are we doing. So in case of, if we use a greedy mapping where we are not being aware, so that is going to be the difference.
But then also the second part for the energy, where do the benefits come from? Just from finishing earlier and hence leaking less? Or is it
the benefit is in two parts, because we have smaller router ports. The power consumption of each of this communication actually reduces. So while the time they're running equally, so we might have to wait longer if we are not doing this hardware software co-design where we map along this contiguous path that we actually created. So that's where we get the benefit. So the same workload would take longer time because we are waiting while it is getting inferenced.
Okay, thanks.
Okay.
I just want one clarification. You use the word explainability. What does that mean basically in this context?
So here, just this idea, the Floret architecture, the reason why it's performing better, it comes in because of the reason why it's performing better when compared. The explainability, just the word as in like why it performs better, not into the, yeah.
Very excellent work. So I think the methodology you apply to NOI can be also used for NOC design. So what are the new challenges that should be solved for NOI design?
I can give you an example. So we can imagine this space filling curve in a 3D IC setup also, where we have this NOC design where the traveling would depend on, you have X, Y, and Z axis where you can probably travel. So the size of the search space becomes increased. So that is one possible scenario where we can do the space filling curve architecture.
You mentioned workload aware, right? So you are designing a different architecture for each mix of workloads?
So this is one fixed architecture. So the workload awareness, the word comes in from this contiguity that we are maintaining due to the Li to Li+1 nature. So it is agnostic to whatever CNN we might use, because all of the CNNs have that Li to Li+1 primarily. The skip connections travel through this NOI.
So you optimize based on, not on a fixed set of
yes,
workload.
The architecture is fixed to what we were.
What is the workload model then? Like,
so workloads vary from, if I go to one of the previous slides, I can show this figure as an example where each of these are mix of different workloads, which were like 16 ResNet 34 are running, after which the concurrency is VGG 16 and so on. So this is one example where we have.
So you don't
like
optimize for each of this set of.
No, the architecture is fixed. We run these on multiple different to see how robust our consideration is when we have different set of CNN tasks coming in.
Thanks.
So it's fixed NOI, one single architecture for one system size.
So in your experiments, actually, you are assuming that all applications are
On one single
at
architecture.
once, and you just measure the finish time of that.
Yes, we measure the power consumption and the latency at the.
So is it
correct.
possible to like add or delete some neural networks during the execution?
So
Okay.
during execution, all of them are running. So the time that we actually give in the time of execution is when the last one has finished.
But my question is that like, so when you map this network into your SFC curve, right?
Right.
Then
So
how,
it gets
how
mapped.
could you map? Like, is there any problem of like, so the remaining SFC is not.
So the way the
Yeah.
mapping, we consider that the mapping is happening in O1, where the amount of workload that we can fix in one single compute resource that is available, say example, the 100 chiplet, we might be able to map until NN11 as an example. And then the rest one is happening after the first part runs through.
Any other questions? Okay, then let's thank speaker again.
Thank
Okay. Actually, I forgot to introduce myself. I'm Professor Sunoya from Seoul Regional University. I was supposed to introduce myself in the beginning. Anyhow, okay, let me introduce second speaker. Second speaker is Chi-Xuan Yan, National Taiwan University and academic senior. He received the BS degree from the Department of Electrical Engineering, National Taiwan University in 2015. And the MS degree from the Department of Computer Science and Information Engineering, the same university. He is currently pursuing the PhD degree with the Department of Computer Science and Information Engineering. He is also research assistant with the Research Center for Information Technology Innovation, Academia Sinica, Taipei. His research interests include embedded systems, embedded deep learning, and intermittent computing. Already? His title is Keep in Balance, Runtime Reconfigurable Intermittent Deep Inference. Yes. Okay. Okay, let's welcome speaker.
Okay, thank you for the introduction. Then now I will present our work. Our work is titled as Keep in Balance, Runtime Reconfigurable Intermittent Deep Inference. They can maintain the inference performance for intermittent system under dynamic power conditions. So let me briefly introduce my slide. First, I will introduce what is intermittent system and why efficient intermittent inference is important but challenging. Then I will talk about some backgrounds, why runtime reconfiguration is necessary for intermittent deep inference. And then I will propose our approach that is called DIBEL, and it dynamically reconfigures the intermittent inference engine to maintain a balance under dynamic power conditions. Then I will present some experiment results and then conclude the talk. Oh, sorry. So let me introduce our hardware platform. Here, energy harvesting is a more popular technique. And in such a system, the system is powered by ambient energy like this. It's weak and stable. So applications running on such systems will encounter frequent power failures, and they are running intermittently. So, and also there are many approaches for intermittent deep inference on such systems. And to achieve inference across multiple power cycles, they need to preserve the inference progress during an inference and then recover the progress upon power resumption. And both steps can take a high overhead, especially the overhead can change with different power conditions. So overall, we need to maintain a good inference performance under intermittent systems. and especially when the power is weak and stable and unpredictable. So let me introduce the system. Here, usually we use tiny microcontrollers for intermittent systems, and those systems come with very tight memory constraints. So for such a system, we put data on non-volatile memory and fetch the data into volatile memory for computation. For each tile, we will fetch the data, and after the computation, we will put the output back onto the non-volatile memory. And usually the performance of non-volatile memory is much worse than volatile memory. So when data is fetched into volatile memory, we will try to keep it inside the volatile memory as long as possible, like among different tiles, so that we don't need to fetch data from non-volatile memory again and again. And this is called data reuse. And the amount of data reuse can change. There are many factors, and one of the most important factors is that the inference configuration can change the data reuse performance. So here's an example. Some data from the first tile is reused in the second tile. And here we show that the tile size can affect the data reuse amount. And in general, we want to use a larger tile, so more data is fetched into VN and then reused in the VN as long as possible. So the performance will be better. And for continuous, that's the story for continuous system. And for intermittent system, it's slightly different. First, let me show how intermittent system works. In this picture, we can see the intermittent system harvests the ambient energy to the system. And then when energy is enough, it will power on, like in the green block. And it runs for a very short time, like a few milliseconds to a few hundred milliseconds. And then the power is failed. And then in another cycle, maybe it will harvest more energy and the power cycle is slightly longer, but in general, it's still shorter than 1 second. So on such a system, because the power cycle is very short, and for complicated application like intermittent inference, we will need multiple power cycles to complete. And as I have said, intermittent inference will need progress preservation to preserve the progress onto NVN during the inference, and then do some progress recovery to resume the inference execution after the power is resumed. And during progress recovery, there is an important factor that data fetched into VN is lost during power failures. So in the next power cycle, data is refetched again from NVN to VN. And this is a dominant factor during power recovery. Also, the amount of data refetch changes with the different configurations like tile size or some other factors. And overall, we want to maximize data reuse and also maximize the tile size on continuous power systems. But on intermittent power systems, it may not be a good case. Here is an example. When the tile size is small, then we only have low data reuse, but we also have low data refetch cost. On the other hand, when power is, when the tile size is larger, then we can reuse more data when power is more stable. But when power fails, we also need to fetch more data from NVN to VN and incurring a high cost. So we need to take a balance between data reuse and data refetch costs for intermittent systems. And here we further make a key observation that the balance between data reuse and data refetch can change with the intermittency level that is affected by the input power strength. And here is an example. When the power is going weaker and weaker, then the balance point of data reuse and the data refetch moves to a smaller tile size. That is because when power is weaker, then there are more power failures, and data refetch cost is higher and dominate the overall latency. And on the other hand, when the power is stronger and stronger, then the tile size, the best tile size will be larger. That is because data reuse will dominate, just like the case for continuous power systems. So our key observation is that we cannot use a fixed configuration that maximizes data reuse for intermittent system. Instead, we need to dynamically reconfigure inference engine and use different configurations so that the performance can be maintained under dynamic power conditions. And now let me introduce our approach. Our approach is Codes+Isss, and it is try to maintain the balance between data reuse and data refetch. And that is done dynamically at the runtime and change the inference configurations to different values. And here we use a separate plugin module that can be easily integrated into existing intermittent inference engine. So we provide such a simple API and for easy integration, so it's applicable to different approaches. And in our system, there are two key components. The first one is the performance estimation, and the second one is runtime reconfiguration. Here, the runtime reconfiguration will use feedback from performance estimation component, and then it will also use some heuristics from design time analysis. And those components are invoked at different time. For example, at each layer, for the start of each layer, the inference engine will invoke the runtime reconfiguration component to find a new good balance between data reuse and data refetch, and then apply it for the current layer. And then at the start of each power cycle, progress recovery will occur, and then it will invoke the performance estimation component. That is for estimating the current power level. Is it strong power or weak power? And to realize such a design, we need to address two key challenges. The first one is how to easily and accurately estimate the performance for different configurations. This is not trivial because there are two main factors for the performance. One is data reuse and another is data refetch. And both factors will be affected by the input power strength. And the other challenge is that how can we find a good balance at runtime? Because at runtime, we need to keep the overhead minimal. Otherwise, the benefit will be gone. But this is not trivial because we need to check many inference configuration parameters. And each parameter there are many possible values. So the configuration search space is very large. So to address the first challenge, we propose a metric that is called usage span. And this is a proxy metric for estimating the intermittent inference latency. And here the idea is to estimate the non-volatile memory access cost because it is dominant in intermittent inference. And among the costs, there are two key factors. One is data reuse and another is data refetch. Here, the data reuse cost is estimated by the number of data access to the non-volatile memory, and data refetch is estimated by the number of power failures during the inference. And for the second challenge, we propose a lightweight runtime reconfiguration algorithm. Here, the algorithm can capture the moving balance between data reuse and data refetch under dynamic power conditions. And the algorithm includes two steps. The first one is cut down the search space significantly. Here, we use some design time heuristic that is derived from usage span analysis. In this case, we can see there are some patterns for the usage span curve. So we only need to consider some points on the curve, not everyone on the curve. And after reducing the configuration space, we will check each configuration in the remaining space. For each configuration, we'll use usage span and the level of intermittency, those two information to determine the performance. And the level of intermittency, it is from the intermittent inference engine by deriving the intermittency level from the progress information. Okay, so we propose some simple approach to show that dynamically reconfigure the inference engine is good, but there are still some possible improvements. For example, we can improve the accuracy of the performance estimation metric. We can consider more hardware constraint and hardware costs like DMA or some other costs into the equation. But This will reduce the generalizability. It may not work on different hardware platforms. And another way is to improve the search algorithm. For example, we can consider multiple configuration parameters at once. However, this may increase the runtime overhead. So let me introduce my experiments. We use an Texas Instruments microcontroller MSP432 as the intermittent system, and we run our experiments on different power conditions. That includes static power conditions and some dynamic power conditions where the power strength changes with time significantly. We also use a few DNN models that is commonly used in tiny ML applications. And those models come with different sizes of search space. Some are larger and some are smaller. We also run our experiments on different non-volatile memory access speed. That is the full access speed of the used chip and the 75% of speed of the chip. And finally, we compare two approaches. One is stateful. Stateful is an intermittent inference engine recently published. And our approach, Diabell, is integrated with stateful. And we want to show how Diabell can improve over a recent published intermittent inference engine. And here, let me show some of the power traces used in our experiments. There are some different kinds of traces, and some are more dynamic and some are less dynamic. For example, RF. For RF, the level of intermittency and the available energy in each power cycle changes with time very significantly. Okay, so under these conditions, let me summarize our experimental results. Here, from figures, we can see the intermittent inference speed is improved by 1.02 to 3.26 times. And particularly in some cases, the inference for stateful does not even complete. That is because a fixed configuration may use a large tile size. So it requires a higher energy than the energy harvesting can provide. And overall, we can see the improvement is higher for larger and data access intensive convolutional neural networks under weaker power. And also note that we want to show the variation of intermittent inference latency is minimal for Diabell. Instead, for stateful, the variance can be quite large. That is because Diabell dynamically balances the data reuse and data refetch cost. So overall, it can achieve a similar performance for different conditions. And here we show the runtime overhead of our mechanism. From these figures, we can see all overhead are below 1%. And for those overhead, we can further break down the overhead into two components. One is the light blue overhead that is related to the data tracking cost. Data tracking cost is when the intermittent inference engine passes the progress information to our system and to estimate the intermittency level. And another one is the runtime reconfiguration algorithm itself. And here we can see the tracking overhead dominates the overall overhead because it requires NVM access. It writes data and reads data from it, and it is performed in every power cycle. Anyway, overall, the overhead is still small in all conditions. So from experiments, we show that dynamic reconfiguration can improve the performance significantly, but there are still some cases where the improvement may be limited. For example, when the volatile memory space is very small, then only smaller tile sizes are feasible. So the search space is constrained, and only a small gap can be achieved by using dynamic reconfiguration compared to a fixed configuration. And another case is when the non-volatile memory access is very fast. In this case, the data refetch cost may be negligible because even though we fetch much data from non-volatile memory, the overhead is still quite low. So data reuse cost is similar to the overall cost, and maximizing data reuse is already feasible and suitable for intermittent systems. But we want to emphasize that such cases are rare because modern microcontrollers usually comes with a large volatile memory, and the capacity is large enough to have a large configuration search space. And the non-volatile memory is generally much slower than computation, especially when an external non-volatile memory is used. Okay, and here let me show a simple demo video. In this demo video, we will run Diabeo and stateful. And here the system is powered by the lamp and then an energy harvesting module to collect the energy. And we show the system information on the user interface, including the progress and the system status. And here we can see that with Diabeo, the intermittent inference can run faster. This is because we achieve a lower NVM access cost. And Diabeo will finish the inference earlier than stateful. Okay, and let me conclude my talk. Here we show that runtime reconfiguration is very important for intermittent deep inference. And we propose an approach to dynamically reconfigure the inference engine so that it can maintain the balance between data reuse and data refetch. And in the experiments, we show that we improve the intermittent inference by 1.02 to 3.26 times, and the overhead is minimal. So we hope this research can motivate in some new research direction that adapting existing approaches to dynamic power conditions. And this is complementary to existing efforts on intermittent friendly models. And we also make our project open source. So it is much easier to develop in some efficient applications under dynamic power conditions. Okay, thank you for listening.
There are questions from the audience?
Hi. So the algorithm that you used to find an optimal value for refresh and the data reuse, what is the energy overhead of that algorithm?
Energy overhead, we didn't measure it, but we also expect that.
Because you mentioned about the time overhead, the overhead that you face in terms of time, but what about energy?
This is measured in latency, and we expect that the energy overhead should be in a similar order, like lower than 1% or around the 1%.
Because you are talking about intermittent computing, and if the energy source is not stable and your power is not stable and the extra algorithm is consuming your power.
So we need
what should be the profile of that power?
We need to keep, so we need to keep the overhead very low. What do you mean by profile and power?
By profile, I mean like the overhead.
The order?
The overhead. Did you measure the overhead?
Overhead. How do we profile? We run the Diabeo approach and then measure the latency. This is in terms of latency. And then we run it without Diabeo and calculate the difference. So this is how we calculate overhead.
The energy overhead, the power overhead.
We can do something similar for energy, but here we only measure the latency overhead. That's a good question. I think we will measure the energy overhead later.
And the second question, which is related to that in case of a multi-core system, what is your protocol for writing back the inference progress that you made from volatile memory to non-volatile memory? In case of a multi-core system, what is your protocol for that?
Protocol for writing back the result. Here we use the stateful inference approach, and there is another story. For stateful, the amount of data to preserve the inference progress is minimum, and we only write one value for each neural network output. So we only need very minimum non-volatile memory access.
Thank you.
Okay, questions at the back. So,
My question would be, in what applications does it make sense to, you have fresh input to do an object detection or recognition problem to restart at all in case, for example, the power does not come up very soon, you can give no upper time guarantee that how long you compute your latency is not bounded, right? So wouldn't it be better in many scenarios that instead of starting at the current state, using fresh data when power is available again to find an actual recognition on fresh data than to recapitulate when there's no bounds on the time you need to recover when power will be available again?
The application, that depends on your requirement. For example, we want to do some intelligent things on Internet of Things application, Internet of Things devices. On such tiny devices, there are still some cases. For example, we can measure the human health conditions, and also we have some smart farming project, and we can measure how plants are grown and what is the sun conditions, things like that. And in such applications, we don't need to run the application continuously. We can measure, for example, for smart farming, we can just measure once per day and run some slow inference on it. And there's no hard time requirement for that.
okay, I have a question. Isn't it possible to consider the remaining energy to make a decision? So I'm not sure how do you stop the applications after power off? Then if we actually wait until some sufficient energy is stored, right? And then we can actually reduce the number of powerful situations, right? Why don't you?
Here in our system model, the application are passive. We cannot control when the power will fail and when the
power is accumulated, right? Energy is accumulated. So why don't you start your application only after sufficient energy is stored and running?
Yeah, that's another research direction in intermittent computing. And here we want to mention that in our case, we try to do more things when there is energy available. So we don't wait, we just run whenever there's energy. And because there is also some benefit in our system. In our system, we only need very few energy to run a few steps. So we don't need much energy.
Okay, since time is up, let's thank the speaker again. Okay, our third speaker is Chengpeng Jia from University of Otago. Chengpeng Jia is currently a PhD candidate at the University of Otago in New Zealand. His research focuses on accelerating artificial neural networks on optical systems. His current research interests include optical neural network, optical interconnections, parallel computation, designing efficient machine learning, optical interconnects, and DNN accelerator architecture. The presentation title is Stadia, Photonic Stochastic Gradient Descent for Neural Network Accelerator. Ready? The first one. Yeah, right. Could you help me to? No. Okay, well, why don't you start your presentations?
Good afternoon, ladies and gentlemen. My name is Chengpeng Jia, and I'm from University of Otago. And I'm delighted to have the opportunity to speak before you today. The topic of my research, stochastic gradient descent for neural network accelerators. I'd like to divide my presentation into four parts. Let's go motivation of our research.
As we all know, with the development of artificial intelligence, deep neural networks have been widely applied in various fields such as computer vision, speech recognition, and with expressional inference accuracy. However, with increases in both the scale and the complexity of DNA models, the number of parameters is in the latest models has exceeded trillions. For example, Google Switch Transformer has 1.6 trillion parameters, and the GPT-3 models has 175 billion parameters. And the amount of training data has also increased significantly, expanding from 40 gigabits to 50 terabits. The demand of people for the large-scale training and the large-scale model keep growing, and the traditional approach of increasing frequency have hit the broken edge of the power consumption war, and it's urgently to explore new computing technology to accelerate the training of large DNNs. Photonic computing, which encodes data on light wave for computations, has emerged and exciting ways to accelerate DNA training with low power and light speed processing. In 2020, Lightmet released the world record photonic chip to accelerate the matrix multiply multiplication operations, achieving 10 times faster with 90% less energy compared with the GPU. And in 2021, IBM designed a photonic tensor that can execute trillions of max per second. So what is silicon photonics? Silicon photonics is an application of photonic systems that use silicon as an optical medium. And actually, photonics has been used in such wide fields. If you look at where is the photonics used to computing nowadays, it's almost in the communication. And that's logic because photonics is really good for transform information, and optical links is very simple. You take a light source like laser and you put a high-speed electrical signal onto it, and then the output you covered with a photo detector that modulates the light back into the high-speed electrical signal. And this electrical signal can be up to 100 gigabit per second. And your light actually have much larger bandwidth than this 100 gigahertz. In electrical signals, we have 10 gigahertz of bandwidth for modulation and 5 gigahertz for radio frequency carrier. But in optical domain, we have 40 terahertz of bandwidth. And on the same time, in the short distance data transmission, the energy efficiency of optical signal can be 10 terabits per second per watt. And while the efficiency electrical is only 1 terabit per second per watt. Due to the advantage of photonics in high bandwidth distance, low power consumption, and people want to integrate the optical device in chip level. This technology has developed repeatedly. However, previous optical neural networks mainly focus on accelerating DNA inference and forward propagation, but the equally important backward propagation of DNA training has not been well studied. So our work aims designing optical back propagation accelerator based on measured optical device. And let's go to optical device. We use micro-sensor interferometer to perform matrix multiplication through interference. and the optical signal carrier, the data is equally slipped into two arms of interferometer, and the MZI make destructive interferometers by applying a voltage to the two arms, which cause a different phase shift in each input signal. Based on the value to be multiplied, two different voltage are applied to the phase shift in the two arms to generate a different phase shifter. And the application of the input data can be realized only by attenuating the signal without adding additional light source for power amplification. So the output power of signal is as this equation, and where P is the power of optical signal. So we use micro resonance to couple the input signal into a single waving guide, and the power of all optical signals in the same waving guides is considered to be the sum of the input out optical signals. Look at this picture, and the red input light can be coupled into the ring and leave from the drop port, and whereas the blue light continues propagating unimpeded by the MR to the through port. And since interference is avoided in the vector waveguides by making each signal travel with different wavelengths, the red and the green lights can be combined, and the total optical power can be detected using a photo detector to perform an additional operation. So the next key device used in our work is balanced photo detector. Balanced PD contains of two photo detectors connected with each other to cancel photoelectrical currents. The two photo detectors are used to receive the accumulated input signal, and the field utilized to balance the direct current of photo current that arrives the PD. When the intensity of beam changes, the difference between the two beams cause the photo detector to become unbalanced and output the net signal at the end of the BPD. And any imbalance between the input beams detected by the BPD is amplified and is output as a received signal. And the output current is as this question, when P positive is the optical power of positive signal, and the P negative is the power of a negative signal. Let's move to our key ideas. Backpropagation is a common method used for training neural networks. It involves computing the gradient of the loss function with respect to the network's parameters to adjust the weight, enabling the network to learn how to perform specific tasks. The key idea of backpropagation is to propagate the error signal backward from the out layer to every layer of the network to calculate the contribution of each parameter to the loss. In our design, we use mean square error to calculate the loss, so the gradient computation can be derived as accumulate of hx subject y multiply x. And this can be considered as a matrix multiplication. If we implement this equation in optical domains, optical gradient descent can be realized. So based on this equation, we design optical stochastic gradient descent using MR and MZI. We call it stadium. And the data are uploaded into optical by two ways and presented by the optical power. The first way is directly modulating the input wavelengths, and the second is applying a voltage to the MZI as mentioned above. And as we can see, stadium contains n horizontal waveguides service as input function, and 4 vector waveguides as accumulation function. Each input waveguides contains 2 MZIs to perform multiplication between the input signal Hx and Y with the value of the training sample X. And there is a MR at each waveguide intersection to control whether the input signal should continue propagating in the input waveguides or should be coupled into corresponding accumulation waveguides. And the 4 waveguides are divided into 2 groups to accumulate the signal carrier Yx and Hx respectively. With each group, 1 waveguide is used to accumulate signal carrier positive value of training sample X. The MR are dynamically activated to control the accumulation of the signals that carry the product on corresponding waveguides. And each group of waveguides is connected to a BPD. Hence, the difference between positive current and negative current at the end of the BPD will output the sum of the absolute value. Obviously, stadium with large setting on N will provide better pluralism, but will also increases the wavelength requirement, crosstalk, and error size. In our paper, we use stadium N to present stadium with N input waveguides. So this slide depicts proposed the optical architecture for deep neural network training, utilize the propagation algorithm. In order to enhance data pluralism, the architecture integrated multi-process elements and stadium into a single chip, especially PEs are employed for forward propagation. With each PE, you are able to establish connection with any stadium. As such, multiple layers of DNN can be operated by different PEs with photonic broadcasting parallel gradient descent for each layer. The Ys are replugged into the stadiums, which subsequently fired the optical element to execute the gradient calculation once the output signals of PEs arrive. Additionally, each stadium has a small cache that store preload filters, Ys, and update the Ys. And the output values of stadium are converted to a digital signal by an ADC and then uploaded to the cache. And the neurons in the cache are repeatedly fired until the training is complete. To imagine the efficient data distributed for parallel computing, we design a data flow using an instance in CNN acceleration. As we can see, the different data are represented by different color, and in which input value is blue, white is green, and the training sample is gray. Step 1 is responsible for inputting an input value and the white mixture to present forward propagating and nonlinear activation, and the output is transmitted to a stadium for back propagation in step 2. And in our data flow, propagation reuse input value X in stadium and can reduce the number of modulation, and that can significantly reduce the time and power consumption. So let's move to evaluation. To analyze the feasible of analog computing, we evaluate the precision and scalability of stadium. Our exercise of precision primarily consists two sources of precision limitation. The first is loss, and the second is noise. The propagation of light through a photonic device introduce the transmission loss that impacts the precision of stadium. And the light transmitting through the MR grid can lead to crosstalk. And for the noise in photonic system refers to any unwanted factor can affect the precision and reliability of photonics computation. The first is relative intensity noise, and then is a short noise, and finally is thermal noise. To evaluate the precision of the system, the 10 bit of precision is introduced. As shown in this picture, stadium can realize the 10 bit of precision under the constraint of noise and loss, and the stadium can achieve a 176 horizontal waveguide dimension in 8-bit precision resolution. To evaluate the time and the energy efficiency of stadium, we simulate the time and energy consumption of their training on Python. The electric system in stadium is evaluated by 7 nanometer technology in FinFET. We use metric device we use metric electrical device and optical device that can have dimension to be fixable for the simulating and the implementation of optical gradient descent. So we compared our stadium-based architecture with recently photonic backpropagation accelerated BP light, which is a photonic and memory stir based accelerator with complete backpropagation architectures, and as well as a GPU platform. This table shows the footprint and power breakdown of our stadium-based architecture with total error estimate as about 100 square millimeter, and this meet our expectation as optical components still take up more space than electrical components. And MZI control contribute about 9%, which is largest error among the computing components. The total power of all components is about 5.71 watts. Among each digital analog converter use the most power of 3.98 watts, which contributes about 70% of total power. Thus, DACs are more likely to become the bottleneck on both latency and power. Moreover, the power cost of data conversion between optical and electrical even exceeded power cost of optical computation. And these two pictures show the propagation lengths across the Lannert, AlexNet, VGG90, Google Lannert, and the ResNet 80 architectures for BP Light and our accelerator based on Stadium 9 and Stadium 8. On average, Stadium 9 based architecture can reduce the latency by 9.7 times and outperformed by 147 times compared to BP Lite. We use 8-bit integer quantization to train the clarification task. We evaluate the impact of 8-bit integer quantization on the accuracy of the training neural networks. And our stadium accelerated significant gains in the latency energy and the computational efficiency only result a mirror drop of about less than 1% in the top 1 accuracy on 4 benchmarks on average. Let's conclude our work. And optical computing has advantage of high bandwidth and energy efficiency in DNA accelerating. While the existing work on optical neurons mainly focus on DNA inference and forward propagation, but the equally important backward of DNA training has not been well studied. So we propose studying a novel analog and scalable silicon photonic-based gradient descent unit for back propagation. And based on stadium, we design a neural network acceleration architecture for back propagation. And furthermore, we developed a data flow to explore the multicasting capability of photonic communication to achieve the high data parallelism. Thank you for listening.
Okay, questions from the audience?
Could you explain the experimental procedure in more detail?
Oh, okay. Our experimental setup is involved building entire chain on using Python, and the electrical device is the parameters of electrical device and by the 7 nanometer FinFET tools, and we broke down the every optical device energy and the time, and the entire system consumption can obtained by the each device and all processing on the DNA training.
Okay, thank you.
More questions?
Okay, thank you for your nice presentation. So I wonder how fast is your simulation work? Because of each approach for each step size, or from the computation power is about 29 times than the existing memorized architecture, but we don't present in this slide. Okay. So in reality, this approach is suitable for training the DNN workloads. Is not in the phase of inference, isn't it?
Yeah, this is our design is special for the back propagation processing. It's not for the forward propagation.
Okay, thank you.
Thank you.
So in this slide, which GPU you are using? Yeah, in this slide, GPU performance is too low. I mean, less than 18 takes only, is 100 milliseconds. So what GPU did you assume?
GPUs this GPU is based on the existing in HPC GPU platform for 1080 is maybe about faster. Sorry, we don't show the but in my paper, it shows the performance of our architecture. Yeah.
Okay.
Thank you.
Okay. Since time is already up, so I think we can ask more questions in the poster sessions. Okay, thank speaker again. Okay, the last presentation is late breaking presentation, 5 minutes presentation, very short. And if you have questions, then please use poster session. So speaker is Anil Kanduri, Department of Computing, University of Turku, Finland. Anil Kanduri received PhD in computer systems from University of Turku and is currently working as a senior research fellow at Department of Computing, the same university. He was a visiting researcher at the University of California, Irvine in year 2022, and also Politecnico di Milano between 2019 to 20. His research interests are in heterogeneous multi-core processor architectures, distributed embedded systems, and resource-efficient computing methods for HML. Okay, his research is supported by EU Horizon Initiative and Marie Curie IT and Actions, COUT and Nokia Foundations. So his title is DynaFuse, Dynamic Fusion for Resource-Efficient Multimodal Machine Learning Inference. Okay. Okay, let's welcome speaker.
Thanks for the introduction. My name is Anil, and today I'll briefly introduce our late-breaking paper, DynaFuse. Probably this will be an unprofessional wrapped version because I have only 5 minutes. The lead author, Hamid Rasa, is actually tied up with the internship responsibilities, so he couldn't travel, and I'm filling in for him. As most of you are already aware, multimodal machine learning applications use complementary and supplementary information from different modalities in order to improve the prediction accuracy. Each of these modalities in general by nature have a certain inherent insightfulness, and the fusion methods actually use these metrics to combine the results in the late fusion phases. But the reality is that some of the applications which have data sources as analog sensors at runtime are prone to input data noises. And despite this fact, the fusion methods continue to use a design time determined fusion weights. And probably we end up inflating some of the noisy modalities, the significances of them. Incidentally, we also might deflate some of the more insightful modalities at the runtime. We can actually look at the a more quantified version of such an application. In this case, we ran a toy human activity recognition application with 3 modalities. One has the accelerator and gyroscope at foot and thigh, and the other one is the EMG modality. Obviously, the EMG modality happens to be the least accurate under ideal conditions, but also we can notice that this consumes a significantly less amount of energy because the circle size actually shows the energy consumption of the sensor. But we injected noise selectively in the most accurate modalities just to demonstrate the consequent effect. What we see is that what was once determined as the most accurate modality with noise ends up being the least accurate at the inference time. And incidentally, the least accurate EMG modality now happens to be all of a sudden the most preferable or more accurate given the runtime dynamic conditions. This motivates the fact that dynamic weights for multimodal fusion can be or should be set at runtime by understanding A, the runtime input data quality, and B, perhaps an energy consumption metric if that is relevant, perhaps in a wearable or a mobile device context. To this end, we implemented the DynaFuse framework, which tries to incorporate the runtime monitoring of input data quality. We implemented a lightweight signal quality assessment module that quantifies the effect or that quantifies the quality of a given data sample in a lightweight, quick fashion. And then we combine this with the design time priorities in order to come up with a updated modality weight configuration. And based on the vector we generated as the updated modality weights, we select one or maybe more than one models from a pool of pre-trained unimodal models. And then we fuse them using the updated weight vector, and then we proceed with the inference. To evaluate, we picked two multimodal M-health applications of human activity recognition and stress monitoring. Both of them have at least 3 modalities, and they are collected by wearable sensors. And as you see, the red line actually represents the state-of-the-art static modality weight assignment for 3 of the modalities. To test our approach under some noisy conditions, we generated 40 batches of test data samples, and each of these batch has a variable noise that is injected across all the modalities in a random fashion. Well, the static weights automatically is just the straight line, whereas the scattered weight assignment shows the dynafuse's efficacy here. And in order to emulate also the energy consumption or the demand behavior, then we created 3 different modes of energy demands, maybe low energy or nominal and high energy demand modes, so that we force the dynafuse also to insert the priority in terms of energy efficient sensing as well. So then we toggle between either the most accurate one or the most energy efficient one. But in the end, we end up securing a weight that is probably the most accurate within the lowest energy consumption as possible. We had about 20% gain with the human activity recognition and roughly 30% of energy gains in both human activity and the stress monitoring. But the accuracy gain in case of stress monitoring is only 3%. This is largely owing to the fact that whether the modality weight assignment dynamism translates into a prediction accuracy or not depends entirely on the application's inherent resilience, A. B, also the kind of noise characteristics and the sensors that we are dealing with. So to look more into this work, we are currently exploring e-health applications, which includes also image and video data and autonomous driving case studies, maybe to find out if such an assignment makes much more sense in a more realistic scenarios. I think I don't have any Q&A slot allocated. So if this really interests you, I'll be at the poster upstairs so we can really chat up there. And thanks for your attention and have a great rest of the week, ES week.
Okay, thank you. Okay, this is the end of this session. Then please meet speakers in the poster session if you have more questions. Thank you.